Calculator problem today. The infamous boat in the river problem. Learning target is again that you will investigate real world motion. So one of the things we've gotten lost a little bit in this whole distance learning thing is normally have an entry task, which I call a do now. And anyway, it's something that's a little bit challenging to do with the Zoom. So we're going to do it now. So I've got a problem here for you. I spun the random number generator. I came up with the numbers that you see on the screen here. I got 8 and 14. You're going to have a chance to do this with a different set of numbers in just a minute. So I just read a couple of vocabulary words, make sure we're clear on. So a boat is traveling downstream in a river. Means the boat and the current are both moving the same direction. The river current is 8 knots. Speed of the boat's motor is 14 knots. Navy people have their own special vocabulary, and knots is one of these words. You could think of it like miles per hour. It's essentially the same thing, but not quite. Navy people. Anyway, their job is to find out what is the boat's net speed relative to shore. Our little observer here standing on the shore, as she watches that boat go by, how fast does it appear that the boat is moving to her? Wow, that was a long drink of coffee. All right. Well, now that you've had a chance to do it on your own, nice work. Let's take a look at this one. Um, so the boat and the current both going in the same direction. So we'll start with the current is at 8. I'm going to add them together because they're both going in the same direction. The boat is red. And oh, that was the wrong click. Equals, and 8 plus 14 is 22 knots. Silent K, but I like to say it's more fun that way. Woo! Awesome. Hey, let's take a look at number 2. A second boat also traveling downstream in the same river, 8 knots. The boat's net speed is 27 knots. What would be the speed produced just from the motor if there were no current? Okay, so I spun the random number generator. I came up with the 8 and 27. You're going to get a chance to do this with your own set of numbers. Go. All right, cool. Hey, nice job. Welcome back. So in this case, what I know is that the mystery number from the boat here and the river current are going to add up to make 27. So you could set it up as like an algebra problem. You could say, like 8 plus x equals 27. Or you could say, you know what, I can see right through that. I just need to subtract. You can do it either way. So I'm going to take that 27. I'm going to subtract the river current, and whatever is left over after that has got to be the speed of the boat, right? So I've got, what do I have? 19 knots for the boat. Nice job. Cool. All right. Well, and a multiple choice question for you. So we've been looking at, our end goal here the whole time we've been looking for the speed it's going to take that guy to run up the down escalator like a little kid, right? So here's our screenshot going up the down escalator. Which of these 4 scenarios most closely represents that going up the down escalator? Would it be a boat floating in a river? Would it be a boat motoring in a lake with no current? C, motoring downstream, or D, motoring upstream? All right, go ahead and make your selections now. Cool. Well, the problem here is that there's still a lot of information we're not quite sure about yet in the going up the down escalator. So we've addressed the boat, but we still don't know anything about the speed of the escalator. So out of these A, B, C, D scenarios, really the only one we know anything about is B, and that's not a match. So maybe we should do another step to find out some more information. So you remember the initial part of the clip where there's 4 of him on the stairs and the escalator and the escalator and the stairs? Well, let's think about just the part where he's on the escalator, moving in the same direction as the escalator. So he's coming down the down escalator here or going up the up escalator here. Should both be the same. Um, which scenario would most accurately represent this case? Floating, motoring with no current, motoring downstream, motoring upstream. A, B, C, D. Make your selections. Lock them in. Okay. Wow, it was frozen there for a second. Nice work. So, yeah, going down the down escalator would be like motoring downstream. That's like what we just did in the do now. And it's going to give us an opportunity to get rid of the boat, to move beyond the boat, and find out that behind him is the river. We got to focus on the river, and we need to find out how fast that escalator is moving, right? And I think we've got a clue here based on what we just did with the do now, because we know that when they're both moving the same direction, the boat and the river are going to add together to create this net speed. And I remember, because I just showed you, I remember this part of the video was also being timed. We can get the time of the man moving down the down escalator. We can use that to get the net speed, right? And once we have the net speed, then we have this net speed and the speed of the boat we can subtract to get the speed of the river. So, so a reminder, we are making some assumptions. We're going to continue working with those assumptions. We're saying that the stairs and escalator both start at the same place. That's supposed to be a highlighter. There we go. And end at the same place. So the distances are going to be the same, whether we're talking about the stairs or the escalator. The shape of the staircase is different than the shape of the escalator case. It's a word I just made up. And that doesn't make any difference, right? The shape is fine. It's the distances that are the same. So we're not going to affect any of our calculations if we're looking at escalators and the other time we're looking at stairs because they're going to have the same distances, right? So just to alleviate any concerns you might have about that. Okay, so um, I've been using a graphic organizer here on my piece of paper that I'm saving all my work on, but you can't see my paper. So I have the speed of the boat. We've done a horizontal speed. As we said, going sideways. It was this distance sideways that he moved divided by the time we got this velocity. So I drew a little triangle. I kept my horizontal speed, or sorry, velocity. So I got a V for the velocity. I kept that on the bottom. And then we also found the vertical velocity. So I kept that on the vertical side of my triangle. We're not going to do anything with the hypotenuse here, so you don't need to worry about that. But just I wanted to share a graphic organizer with you. So what we're going to do next is we're going to find the net speed, the boat and the river together, right? And so I'm going to write that on my graphic organizer. I'm just going to write that down here into the next little space. So we're going to do the vertical net. Sorry, that's actually horizontal. The horizontal net velocity and the vertical net velocity, right? And then once we have the speed of the boat and the net, then we can use those together to get this velocity of the river. But one thing at a time, right? So we are going to need to come up with a time, right? Because in order to calculate the vertical net velocity on the escalator, we've already got this distance. I just mentioned that already. We've got the distance here, but we're going to have to come up with a time that it takes for him to go down the down escalator or up the up escalator. So this is going to be a different time than what we used before. So you got your work from the other day, and that's got the distance that we calculated from the staircase. So we'll go with vertical first. My highlighter color keeps changing. It's weird. All right, but in order to calculate that, we're gonna have to find the time. So let me pull up this video. Let's watch the video, and this time, instead of looking at him on the stairs, we're gonna look at where he hits the top of the going up escalator, the bottom of the down going escalator. Shoot, missed it again. These dance parties are out of control. All right, not far enough. Yikes, that happened too fast. All right, so almost there. So uh, okay, it's probably gonna go way too far. Back it up. All right, come on, man. go down the escalator, down, 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 down. So I can see on the escalator where he's going up, he's still got a couple of steps to go. Sound effects always make math better. All right. Oh my gosh, it looks like he is maybe approaching the bottom step on the way down. And footfall at the top. I can see the footfall at the top. There it is. All right. So we got a time that it takes him to go up the up escalator or down the down escalator. They appear to be the same. It looks like a match to me. And just as a reminder, this colon, I don't know why it's a colon. It should be a decimal place. Okay, so that gives us this time right here. So at this point, you will be able to calculate his vertical net velocity on the escalator. That's the boat and the river together, but only in the vertical aspect. Where'd he go? Cool. And now that you have the vertical out of the way, let's also calculate the horizontal net velocity. So we're going to use that same horizontal distance that you wrote down and saved the other day, and that time that we just saw. Go. Super. Hey, well then, that was amazing math work, and we're just about ready to put this thing to bed. In our next session, we'll figure out the answer we've been looking for.